Hey guys, today we're going to be talking about potential energy. It's going to be a continuation of our unit on energy. That first day in this unit, we talked about all the different types of energy. And then the second day, which was last class, we talked about kinetic energy and how to change it with some work. And we're going to be talking about some similar concepts today, but swapping out kinetic energy for gravitational potential energy. So if you remember from last time, gravitational potential energy is energy that is stored in an object's height. Oops, got my wrong tool. Energy that is stored in an object's height. And it takes into account three things. There are three really important things when it comes to gravitational potential energy. Since the energy is stored in the object's height, that is something that's super important here. So it's going to take into account the height and then also gravity, since it is gravitational potential energy. And then the last thing it's going to take into account is also the mass of the object. So it's stored in the height, but it also has to be in the presence of gravity, and the object has to have mass. So all three of those things are super important. Since we've got those three factors, our equation for gravitational potential energy is going to take those factors into account. But it starts off with a very strange variable, and that is the variable for potential energy, which is a capital U. Who chose that? I'm not sure why they chose it. I don't know. But P was already power. So gravitational potential energy, or any potential energy, is U. And then to specifically make it gravitational, because U is just potential energy, to make it gravitational, it gets a uppercase subscript G as a modifier. So that's going to change it from just any potential energy to gravitational potential specifically. All right, so let's go ahead and label that. That is gravitational potential energy. I'm just going to label that with a PE instead of writing the full potential energy words, but that's neither here nor there. And then you've got the unit is a joule for gravitational potential energy. And that is equal to our three factors all multiplied together. Usually it starts with mass is multiplied by gravity, and that is multiplied by height. Now, if you're an astute mathematician, you would know that multiplication is commutative, which means you can go in any order on the multiplication, so it really doesn't matter that it's M first and G in the middle and then H last, but that's usually how it's written. So we're just going to take our three factors and multiply them together. Now, if you remember, mass is measured in kilograms, so when you see kilograms in a problem, you'll know it's referring to mass. Our gravity here on Earth is 9.8 meters per second squared. No negative is needed here. It's just a constant number, 9.8. And then height is going to be measured in meters. And then once again, down here it says the unit for potential energy and all other energy and work is the joule, which is this capital J over here. So next up, we got to talk about how to do some comparisons based on that. And the comparison question here says, which matters more when it comes to potential energy, the mass or the height? And I'm going to write my equation down here because it is relevant to this. So last class, we talked about kinetic energy, and it was 1/2 times m times v squared. And we said velocity was more important in that sense because it was squared in the equation. So it essentially counted twice as many times. But here in the potential energy equation, we don't have anything that's squared. We have a mass times a gravity times a height. So really, this is a trick question. They matter equally. And this is because they're simply multiplied together. They have the same degree, if you were speaking in mathematical terms. They're both to the first power. They're not squared. They're not cubed. None of that. So they matter equally. And to kind of see that in an example here, we've got two different carts with different masses and heights. One is a heavy cart at 10 kilograms. One's a light cart at 2. Then we've got one that is low to the ground. That's the heavy one. It's at a height of 2 meters. And then we got one that is high off the ground at 10 meters, and that's the light one. So the question here is, which one is going to have more potential energy? The one that has a lot of mass but is kind of low, or the one that is really light but is very high up there? And the answer is, since they matter equally, we've just swapped the numbers here, that they are the same. Now, if you wanted to do the math for that, we'd just be multiplying, right? Mass times gravity times height. So this one here would be 10 times 9.8 times 2, whatever that turns out to be. And this one on the bottom would be 2 times 9.8 times 10. And since we've established already that multiplication is commutative, those two things are going to turn out the exact same. So the mass and the height, they matter equally as much when you're talking about gravitational potential energy. Now we also need to do just kind of a basic calculation example with this before we go on to some more complex stuff. This example says a 15 kilogram box has 300 joules of potential energy. And the question is, what is the height of the box? Now here we've got kind of a dumb system question again. The system here is simply the box. That's all we've got in the scenario. We've just got a box, but it has some potential energy, so it's sitting up above the surface somewhere. Now our givens here are that we have a 15 kilogram box. If you remember from earlier, kilograms means mass. And that 15 kilogram box has 300 joules of potential energy. So that's my capital U, sorry, picking the wrong tool again. That's my capital U with 300 joules for that potential energy. And the question is, what is the height of the box? Now you are welcome to write down that gravity equals 9.8. But that is pretty well understood by now. So if you don't want to write it down every time, you don't have to. You can just plug it in because you know it. So over here on this side, we'll write our equation. UG equals m times g times h. The UG is 300 joules. The mass is 15 kilograms. Gravity is 9.8. And then height is unknown. So the first thing that you should do algebraically here is multiply out your 15 and your 9.8. Now, there are other algebraically valid ways to do this, but multiplying 15 times 9.8 is probably going to be your best bet. Now, since I am not sitting with you guys right now, I'm sitting at home recording this by myself, I am having to stall and actually grab a calculator to do these. I'm not used to having to do that. I usually have you guys handle that part. But I've got it now. 15 times 9.8 is 147. So we get 300 on the left side still equals 147 times the height. And the last thing left to do algebraically here is divide by 147. You're doing a division because the 147 is currently multiplied by the height. I did see a lot of issues the other day with some people's algebra where they were subtracting this coefficient number instead of dividing. So make sure when your number is multiplied by your variable, you divide that number out instead of subtract, because division undoes the multiplication. And here I got to use my calculator again. We're going to do 300 divided by 147, and that is a height of 2.04 meters for that box to have that amount of potential energy. All right, now here on the back, we do have to ramp things up a little bit, but we're going to be doing that in a similar way to last class. So last class, we talked about some objects that would start off with a certain speed. Sometimes that was 0. They'd have some initial kinetic energy, and then something would affect that by doing work. So we'd have an initial energy, add some work to it, and that gave us a different energy at the end. We're going to be doing that exact same thing today with potential energy. So this is called the work potential energy theorem. It works very similarly to last class, where we're going to start with some amount of energy, but this time it's going to be potential energy. So we're going to start with gravitational potential, some initial amount, so it gets a little I. We're going to do some work to change that, and in the end, we'll end up with a different amount of potential energy at the end. That's the idea. You're starting with some energy, doing some work to change it, and ending up with a different amount of energy. Now, remember, work can be positive, which means your object's going to get more energy, or it can be negative, which means your object is losing energy. It is giving it away. But just the same as last time, that's not the final story. There is more to it than just that idea. We're going to swap out our generic variable for potential energy for that equation that we used in the front, because most often things aren't given in terms of their potential energy. They're given in terms of their height, which is the directly measurable value. So we're going to start by swapping out the UGI for mass times gravity times h initial, because your mass and your gravity, they're going to stay the same, but your height's going to change. So you need an I for the initial height plus something's going to do some work to it. That could be positive work where it moves up and it gets energy, or it could be negative work where it moves down and it loses energy. And then that is going to equal, instead of UGF, it's going to equal MGH. And that H is going to get a little F to say that we're at a different height, a final height now. So essentially all this is saying is an object starts off with some height. Right here, MGHI is some height. So that gives it potential energy. We're going to do some work to change that, either positive work to gain or negative work to lose that energy. And it's going to end up with a different amount of energy as indicated by this final height over here. So let's see an example that involves that. This one, number 2, says a 15 kilogram object is raised from a height of 2 meters to a height of 7 meters at a constant velocity by a crane. How much work is done on the object? So here we have a crane and an object. The system we want to be the object because that's the thing that's actually having the energy change applied to it. And that's the thing we know the energy or the information about. The crane is the thing doing the work to this particular object. We could call it a box. We could call it a crate, whatever you want to call it. It's a 15 kilogram object. The things we know about this scenario, besides that it's an object, is the mass. That's the 15 kilograms. And it says it's raised from a height of 2 to a height of 7. So we've got an initial height of 2 and a final height of 7. And then the question is, how much work is done on the object? Once again, we're going to assume we're on Earth, so gravity's 9.8. I'm not going to write it down, but you can if you would like to. Our equation that we're using is the one on the right up there, MGHI plus work equals MGHF. We have the mass, that is 15. We have gravity, that's 9.8. We have an initial height of 2. Don't know how much work, that's what the question is asking us for. And then a mass again of 15, a gravity of 9.8, and a final height of 7. So now what we're going to do is a little bit of algebra. The first step that you probably want to do is multiply all your numbers together that you can. So we're going to do 15 times 9.8 times 2. I'll give you guys a second to do that on your calculator really quickly because I know y'all are doing it. You got 15 times 9.8 times 2. That is 294. So your object started off with 294 joules of energy. Then the crane did some work, and that gave it whatever this right side is multiplied together. 15 times 9.8 times 7. That is 1,029 joules. So what this is saying is your object started with 294 and it ended up with 1,029. The crane did all that extra work and gave it all that extra energy to get up to the 1,029. So what we need to do here is subtract off 294 to get our work. That cancels out, and you have a work of 735 joules done by the crane on the object. All right, we get a positive answer here because our object is being raised. It is gaining energy as that happens. Now, at this point, we are going to skip example number 3. That's because I figure some of you are bored out of your minds because you know what you're doing, and we've worked on this kind of stuff a lot. However, if you want the answer to number 3, or if you want to see that solution worked out, you can go look at it in Google Classroom. It's on the notes key for this set of notes, so you can go get it from there if you really, really want that extra information or that extra little bit of help. But we'll look at number 4 because number 4 does involve some more advanced concepts that we haven't covered today. So we're going to look at that one. It says a person moves a heavy 18 kilogram box from a 2.5 meter shelf and places it on a lower shelf. If the person does 245 joules of work on the box, what is the height of the lower shelf? So we've got a person moving a box, but we're mostly focusing on the energy of the box. So that's going to be our system. System is the box. All the things that we know about it are that it is 18 kilograms. That's a mass as indicated by the kilograms. And it's moving from a 2.5 meter shelf. So that's the initial height that's located at 2.5 meters. But this person is going to take it from the shelf and place it on a lower shelf. And that is the key today, the fact that this is on a lower shelf. Okay, so let's think about it. We got an object moving from a high place to a low place. And what we want to do is think about what's happening to the energy, whether it's gaining energy in that process or losing energy in that process. And what really happens is that it loses the energy because it's going from a place of high potential to a place of low potential, and the person's not letting it speed up or anything, because they're placing it gently. So it's going to lose energy, which means the work here, when something loses energy, that work has to be negative. So when this question says the person does 245 joules of work on the box, that does tell you the number. The number is 245. But the situation, the fact that it's moving from a high place to a low place, that tells you the sign of it. So the work here is negative since it's losing that energy. And then we also know gravity is 9.8. And the question is, what is the height of the lower shelf? So that's the one it's moving down to, which means we're looking for a height final. We're going to use the same equation. The setup of the equation is not bad. The hard part of this question is remembering that negative. But let's go ahead and do the algebra out. We're starting with mass, which is 18, gravity, which is 9.8, a height initial, which is 2.5. And then we are taking away 245 joules of energy. So that's minus 245 equals m times g times h again. So we've got 18 for m, 9.8 for g, but now it's the height final that we don't know. So we'll leave that as hf. Then we have to do out all of the math for that. The first thing is the left side, multiplying 18 times 9.8 times 2.5. Now, you could go ahead and subtract the 245 from that in your calculator. I'm not going to for conceptual reasons. Sorry, I can't talk. When you multiply those, you get 441 minus 245 equals 18 times 9.8. 18 times 9.8 is 176.4, which is getting multiplied by the final height. So what this is saying conceptually is that our object started off with 441 joules of energy, lost 205 of that because the person moved it down. And that's going to give us our total potential at the end over here. But currently that's split into 176.4 times HF. Let's go ahead and do that. 441 minus 245 to get 196 equal to 176.4 times HF. And then to solve for HF here, we have to divide by 176.4. When you do that, you get a final height of 1.1 repeating meters, or you could round that off to 1.11 if you prefer. And it makes sense that that's our height because our initial height over here was 2.5 meters and we were supposed to be moving down, and we did to 1.1 meters. So that works out nicely. Now, the rest of today is basically your stock standard physics day. You're going to do your practice, which is 7 questions, though some of them do have part A and part B. And then you're going to enter those answers into the quiz. And you can retake that as many times as you need to, all the way up to 100. However, in your practice, there are some questions that go back to the kinetic energy from last class period, which I know is now like almost a week prior to when you're doing this. But you can go back and look at those notes. You can see those notes in Google Classroom if you need them. So some of those questions are going to involve these same concepts, but with the kinetic energy side. The equations for that should be on the board. However, if they are not, you can find them on the cheat sheet that's in the front of your unit packet, or you can find them in the key to the kinetic energy notes as well. So you guys work on that. And then if you have any questions, I'll be able to answer them next week when I'm back. See you guys later. Hope you're staying safe and staying warm.